So, in calculating the rate of convective heat transfer processes, what I have indicated, that although we have a governing differential equation which requires knowledge of fluid flow, we will not generally solve those equations, particularly when you are trying to address heat transfer between convective heat transfer between solid and liquid, or vice versa. And instead, what we would like to do is to calculate the heat transfer coefficient, and as I have shown you that the rate of heat flow, okay, is given in terms of a heat transfer coefficient and the delta T, in which delta T is the driving force and the corresponding heat flux is Q dot by A H delta T. This is equal to minus K say dt dx. So, this is the flux, this is heat transfer coefficient, differential temperature, thermal conductivity, and the temperature gradient. Now, as I have mentioned that in many classical situations, it is possible to solve the flow equation. It is possible to solve the energy equation, that is the thermal energy balance equation. If you solve these two, for example, a classical scenario, flow over a flat plate, at which the plate is heated to a temperature of say constant temperature of T0 and the velocity is moving with U0. Then by solving these equations applicable to this simplified boundary layer flow, one can show that one can calculate the temperature profile. Okay? So, at every point you can maybe calculate the temperature profile, and then based on these temperature profiles you should be able to find out that what is the slope of the line. And once you know the slope of the line, knowing the differential temperature, what is the plate temperature here, and the bulk temperature which is T sub B, you know the driving force, you should be able to calculate the heat transfer coefficient. So, heat transfer coefficient will come out to be minus K, say I write it in terms of, you can write in terms of partial or ordinary, does not matter here in this case. Okay, the concept does not change, and then you have divided by delta T. So, the driving force is known, wall temperature and the bulk temperature. Bulk temperature is the temperature far away from this solid surface. So, this is the solid surface that I am talking about, the flat plate. Okay, so, the bulk temperature is here, the bulk velocity or the free stream velocity is also here. So, if you know the fluid flow equation, if you know the energy equation applicable to this, we can solve. Once we can solve, we can find out the temperature gradient. So, this quantity will be known from the solution of this set of equations. Having known this, then I can multiply this with the thermal conductivity and I can divide it by the driving force, and then I can obtain that what is the value of H. And in this particular case, we can find out that will come out to be exactly this is a flat plate force convective heat transfer correlation. So, this is the heat transfer coefficient, this is the plate average heat transfer coefficient, which is because the slope of the line varies at every location. It is a function of, if this is the x direction, and the slope varies at every location, which means that the value of H also varies. So, this is called the local heat transfer coefficient, and this is called H is the plate average heat transfer coefficient. So, this correlation actually for such simplified scenario can be exactly derived by solving the applicable fluid flow and heat transfer correlation. But as I have mentioned, for complex scenario like those we encounter in steel making, we will not be able to solve these equations and derive this kind of a correlation from exactly. So, what we are going to do, how we are going to have force convective heat transfer correlation is we are going to carry out experiments, and based on that we will determine that what is going to be the correlation. For example, we can anticipate that this is going to be the correlation, okay, or we can say that the correlation could be something like Reynolds to the power x into Prandtl to the power y, because that is what is expected from the theory, that most of the cases for force convection, this is the form of the correlation. If you, of course, it's a spherical geometry, then as I have mentioned, we will add 2 preceding to this term. And then the task would be to determine its pre-exponent, to determine the exponents x and y, and in order to determine the correlation and say that this is the explicit form of the correlation, we have no option but to carry out experiments in our laboratory and then provide a specific form of this particular generalized correlation. So, this is, for example, for many metallurgical scenarios, steel making cases, processes, we still do not know that what kind of a correlation exactly is applicable. So, we try to take correlations from the literature and make certain assumptions and try to obtain a first hand estimate of the heat transfer coefficient, which may not truly be applicable. And also one more important thing is that this sort of a correlations which are developed for flow of air over a flat plate, okay, but in the case of steel making, we require correlations which would be applicable to molten steel flows, and as you all know, molten steel have largely different Prandtl number than with respect to the normal common fluid like air, water, etc. So, the characteristics of the boundary layer are going to be different, because Prandtl number is a ratio of momentum diffusivity to thermal diffusivity. So, the characteristics of the boundary layer is a function of Prandtl number, and we will anticipate that the characteristics of the boundary layer in molten steel system and air water systems, okay, in which the flowing fluid is air or water, is going to be somewhat different. So, there is some element of uncertainty when we apply this kind of a correlation in a straightforward fashion to steel making systems. So, I think enough is said about convection. We would now move on to the last mechanism of heat transfer, which is the radiation or the radiative heat transfer. So, the rate law, so we know the rate law for heat conduction, which is the Fourier's equation. Then we have rate law for radiation, and that radiation is the Stephen's equation or the Stephen's law, and it says that the heat flux or the rate of radiation heat flow is equal to sigma epsilon, and then we have sigma epsilon. This is, if this is rate of heat flow, then I will say that this is area into theta raised to. So, theta here represents the temperature, but this temperature is in the absolute scale. Epsilon is the emissivity of the surface under consideration, or absorptivity, which is equal. A is the area, and then sigma is the Stephen-Boltzmann constant. As I have mentioned that radiation does not require a material medium. So, it is electromagnetic wave basically, and so without a material medium, heat can be transferred from one location to another location, and this is precisely. Now, if you are talking about radiation exchange between two objects, in that case we would say that, well, Q12 is going to be whatever heat one is radiating, an object is radiating, and it is going to be receiving also some heat from the surrounding. So, we can say that this is going to be equal to sigma E epsilon, and then theta 1 to the power 4 minus theta 2 to the power 4. We must understand that while convective heat flux and conduction heat fluxes are proportional to temperature, the radiation heat fluxes are proportional to temperature raised to the power 4. Now, this essentially tells us that as the temperature increases, the contribution of radiation is going to be extremely large. You imagine for example, solidified slab, which is at a very high temperature, maybe surface temperature is about 1100 degrees, 1000 degrees centigrade, and then you just keep it outside, and on a normal day you have breeze blowing over the slab. So, you have a convective heat transfer also, and the radiation heat transfer also, radiation loss also, and there you can see, if you are talking of this time, this is going to be 1000 plus 273. So, there is going to be 1273 raised to the power 4, okay, and the ambient temperature could be 25 degrees plus 273, which is 298 raised to the power 4. So, the contribution of this term it's an enormous, the order of magnitude of this term is going to be enormous, particularly at elevated temperature. In radiation, for example, one concept comes into the picture. There are many definitions, like for example, a black body. You know what is a black body, what is a gray body, etc. You know the Kirchhoff's law in radiation, and also reciprocity theorems. There are many such theories which one has to know in order to do the radiation calculation, radiative heat transfer calculations. Well, but one important concept which comes to my mind is called the radiation view factor. Radiation view factor, which is very important in calculation. This expression essentially tells us that whatever radiation is given out by an object, it is received by the other object. So one is receiving the entire radiation which is given out by 2, and therefore we have written the net radiative heat exchange between the two objects 1 and 2 in this particular form. But it may be the case that all the energy emitted by an object is not intercepted by the other object. So for example, if you imagine that the this board is an object and I am an object, so I may be radiating energy in all directions, and this particular board is going to be only getting the radiation which is going out from this particular surface. This radiation is going to be intercepted maybe by the wall at the other end. So a part of the radiation therefore is going to be utilized, will be received by this, and this brings us to a point where the view factor is to be determined. For example, if you consider me that this room is one object, or I'm there standing in the room, or you imagine that a furnace is there, and in that furnace I have a solid ingot is placed, then the furnace is radiating energy, okay, in proportion to its absolute temperature raised to the power 4, but all these radiations are going to be intercepted by the solid object. So therefore in this case we can say that the radiation view factor is going to be equal to 1. On the other hand, the scenario just now I have said that I am standing here, the board is behind me, so therefore the radiation view factor between the board and me is certainly not is equal to 1, it is going to be less than is equal to 1, and therefore in this particular case we have to introduce the radiation view factor in order F12, and the reciprocity theorem says that F12 is equal to F21 and so on. So I don't wish to discuss radiation beyond this particular point, but as I said, it is very important in high temperature processes, particularly in calculating heat losses, etc. Conduction, convection and radiation are very important when you would like to address heat losses, when you would like to address melting rates of solids and so on. We will see that I discussed deliberately the heat transfer in a little bit more exhaustively, because the flow of heat and mass are very identical, particularly if you are talking of diffusive transport of material or mass diffusion, or if you are talking of convective transport of mass, you will find that there is one-to-one similarity between heat transfer and mass transfer, because we are talking about a subject of scalar transport. In this particular case, energy is a scalar quantity, okay, mass is a scalar quantity, so there is one-to-one similarity between the two. So let us now talk about the relevance of mass transfer, and once we have adequate knowledge of thermodynamics, fluid flow, heat transfer and mass transfer, we can now calculate the rate of metallurgical processes, and there we go, we will move on to the metallurgical kinetics, and that will be interesting, and we will see how the concepts of fluid flow, heat transfer and mass transfer are applied in order to calculate the rate of the metallurgical processes or steel making processes. Now mass transfer is also extremely important in our case, because we are talking about processing operations, we are talking about transfer operations where there are interactions among phases, there are interactions between metal and refractory, there are interactions between metal and slag, and these interactions precipitate into mass transport. And the driving force for mass transport is actually concentration gradient. More accurately, it is the chemical potential gradient that gives rise to mass transfer. And in many situations, if you are, for example, if I talk about steel making, you have a casting, and then in the casting you have lot of segregation, sand casting, lot of segregation, which you know as a coring, and then you take the sand casting to a heat treatment furnace, and after some time you get a homogeneous structure, because what happens, whatever has been segregated, now there are regions of higher concentration and regions of lower concentration. So under the influence of heat, you are trying to diminish that concentration gradient, and thereby you are causing material to move from a region of higher concentration to a region of lower concentration. You will be talking about mass transport between in desulfurization, where you are concerned about transferring sulfur from metal to the slag. You would be talking about mass transport when you are doing tank degassing or vacuum degassing operation. How? Because you have dissolved gases in the melt, and now you want to try to drive that dissolved gases into the ambient atmosphere. So it is a transport of dissolved gases like nitrogen, hydrogen, etc. from the melt into the ambient. So we are talking about mass transport. So I can go on and on. Okay, mass transfer is a basic characteristics, and beyond mass transfer also we will see that there are chemical reactions involved, and I will completely isolate mass transfer from chemical reaction. Please do not confuse between chemical reaction and mass transport. Chemical reaction means, you know, the combination, bond making of bonds and breaking of bonds. These are the essential features of chemical reaction, but mass transport precedes chemical reaction. First the material has to come to a place, the reactants has to come to a place, and then the two reactants can collide with each other. Okay, then the new bonds can form or bonds can be broken. So mass transfer basically precedes chemical reaction. Mass transfer also follows chemical reaction when the products have to be removed from the site of the reaction. Now the phenomenological law of mass diffusion. So again we have diffusion as the mass transport mechanism and convection, convective. There is one-to-one similarity between diffusion and mass diffusion and heat conduction. So we had Fourier's law in heat conduction. For diffusive mass transport, we have what is known as the Fick's law. And Fick's law states that flux, which could be mass flux denoted by J, or molar flux. Flux of what? Flux of a species I. J is the mass flux, N is the molar flux of a species I. Flux is a vector quantity, so I will specify in which direction. We can say it is equal to minus d del x. And the net rate of transport, we can say, so the flux typically is denoted by this. So I would say that J I x, which is the net rate of transport, or so C could be mass concentration or molar concentration. You can say that it is either this or minus d. When you are talking about mass flux, we are talking about concentration in mass unit. We are talking about molar flux, we are talking about concentration in molar unit. So this is moles per centimeter cube or moles per meter cube. This is could be mass per unit volume, which is essentially is equal to density, or dimensionally equal to density. So therefore this is going to be equal to nothing but area or Fick's law. We must understand that these equations we have expressed in terms of concentration, but in multi-component system the concentration is not the correct entity. The correct entity is going to be chemical potential, because you may have read about the Darken's experiment, whereby it was possible to transfer mass from a region of lower concentration to a region of higher concentration. It is because of the simple fact that in a region of lower concentration actually of carbon, the activity of carbon was higher because of the solutal interactions. Okay, so superficially you see that mass is moving from a region of lower concentration to lower weight percentage value to higher weight percentage value, but in terms of activity or chemical potential, the lower concentration actually means or lower concentration actually is a higher activity or higher chemical potential, and that is how the driving force, more accurately speaking, is not the mass concentration or mole concentration, but we will have to have chemical potential or activity. But while we are talking about only single component, for example, one single component which is diffusing, in that case the concentration, the activity and concentration are synonymous, so there is no issue on that particular. Now, this equation, this is the diffusion coefficient, and again this is like thermal conductivity. We have this diffusion coefficient which is a thermally activated process, so it follows the rate equation like exponential minus q by RT. So, the diffusion coefficient is a state property, just like thermal conductivity, it depends on the temperature under consideration. So, if you know the temperature, you will know the diffusion coefficient, and to know the flux or the net rate of transport, what is needed is the concentration gradient. On a thumb rule, we will say that material moves from a region of higher concentration to a region of lower concentration. There is one-to-one similarity between D and K. So, this is the molecular transport mechanism. Okay. So, therefore, this is the only mechanism of mass transport within solid, but just like the way I said that in liquids, both conduction and convection are going to be operated, okay, convective heat transfer or conductive heat transfer. So, in liquid, we will also see that material diffusion is there as well as convection is also there. We must remember that there is no counterpart of radiation in mass transfer. It is well known, mass requires material medium to be transported, unlike heat, which does not always require material medium to be transported. Now, using this basic phenomenological description of diffusion or Fick's law, we should be able to do a control volume analysis, which we have done already in the context of mass transport or diffusion, and do a balance amount of mass or material coming in through the control volume and amount of mass leaving through the control volume in all three directions, Z, X and Y, plus the net rate of mass generation, which could be because of chemical reaction taking place between two species, should be the net rate of accumulation of mass in the system. So, a similar equation which I have written earlier, if you remember what I have done, I wrote the corresponding heat conduction equation as so that is the expression which I wrote in the previous lecture. The energy balance within a solid object unsteady state. So, the net rate of accumulation of heat is equal to net flux of heat in the x direction, y direction, z direction due to conduction plus the net rate of heat generation. There is a one-to-one similarity now, and I can say that the corresponding mass equation could be so, there is, as we see, one-to-one similarity between diffusion and heat conduction, mass diffusion and heat conduction. See, replace K by D, replace T by C sub I, and you get the same equation as, note that if I take K divided by rho Cp, that becomes a thermal diffusivity, which is synonymous to mass diffusivity. Both of these have unit as meter square per second. So, if you can write one equation, you should be able to write other equation, and also the simplified form of this, just like the way yesterday I have shown that, well, we can say that this is equal to 0 for constant thermal conductivity under steady state condition with no heat source term, the equation boils down to this: divergence square T is equal to 0. Similarly, this equation will also for unsteady state, for steady state case, that means this derivative is 0. Okay, no mass source term and constant diffusion coefficient, this will also boils down, which is nothing but the popular Laplace equation. So, if you can solve this equation now, we should be able to find out that what is the concentration gradient, what is the concentration field, and having known the concentration gradient, we should be able to find out the fluxes, or we should be able to find out the net rate of transport by multiplying the former with the area, relevant area through which mass diffusion is taking place. Just like the way these equations require boundary conditions, that means at the surface of the object you have to have flux or temperature provided. Similarly, for this also in the three-dimensional domain, you have two values of excess, you have 6 different phases, you are considering a three-dimensional domain, mass transport along x, y and z. So, you have domains, x is equal to 0 and x is equal to L, y is equal to 0 and y is equal to say B, and z is equal to 0 and z is equal to H. So, there are 6 bounding surfaces, and all these bounding surfaces you have to specify that what is the value of Ci in terms of either its absolute value or in terms of fluxes. So, given the initial condition, given the boundary conditions in terms of either mass flux or concentration profile, we should be able to solve this equation, and if we solve this equation, we will know C as a function of concentration as a function of distance, and once we know concentration as a function of distance, we can evaluate the derivative and find out the corresponding mass flux along x, y and z direction. Now, coming to convection, again we have the same kind of an equation that we have seen in the context of heat transfer. So, when you try to calculate convective mass transfer rates, so let me just tell one. So, diffusion, where we are going to calculate? So, diffusion, rate of diffusion would be relevant, just like the way I gave you an example of ingot heating for to make to explain the relevance of heat conduction. So, mass diffusion could be completely relevant, or totally controlling the mass flow, for example flow of carbon in a coat structure or in a casting. So, within any solidified object, if there is a concentration inhomogeneity and you are trying to move one species from one location to another location, or getting a homogeneous structure, in that case you can see that within the solid the flow of material from one point to another point is going to be purely by diffusion. On the other hand, when you talk of convective mass transfer, that means the mass transfer is now aided by fluid motion, and whatever I said about convective heat transfer yesterday is going to be totally applicable to convective mass transfer as well. So, therefore, in order to calculate the convective mass transfer rates, it is understood, I repeat again, we will require the fluid flow to be known first. So, having obtained the flow, our objective would be to calculate the mass transfer rates, and the convective mass transfer equation will exactly look the same as we have done in the case of a. So, for example, yesterday whatever I wrote, and today the concentration, once we put in the convection term here, so what we are going to see, the left hand side will look like, okay, let me just erase this, and then this is going to be easy. So, I can write it like this, if you remember whatever I have written. So, this is the original term, and I have, this is a conduction, this is the diffusion flux. So, I have made a net flux expression, and I said that along x direction mass is flowing not purely because of diffusion, because we are talking of convective mass transport, mass is flowing because of convection also, and the net flux was expressed that within this bracket I had this term minus a convective flux, which was something like, for heat transfer I said that this term looks like something like this, and in the case of mass transport it is going to look something like U into Ci. So, therefore, we can say that if you bring this term here, you can look at your notes and then appreciate the similarity, then say the first order derivatives, and then we have U into Ci. So, this is Ux, then in the y direction we have U into Uy into Ci, and then in the z direction you have uz into Ci, and then we have this particular expression. Okay, this is no more relevant. I just wanted to explain to you. So, these are the convective fluxes, and just when in the previous lecture when I wrote the corresponding heat flow equation, first equation I wrote was that I brought in another term here, and then in the second step I transported this term with a negative sign to the left hand side, and this is the convection along the x direction, this is the convection along the y direction, this is the convection along the z direction. More specifically, convective heat transfer along x direction, convective mass transport along x direction, convective mass transport along y direction, and convective mass transport along the z direction. So, the same sort of an equation. We have 3 terms on convection, 3 terms on mass diffusion, 1 source term, and 1 unsteady state term. So, we have 4 terms on the left hand side, 4 terms on the right hand side, exactly the same equation as you would encounter in the case of convective heat transfer. So, the same logic stays that for every problem we are not going to solve this kind of an equation. We need a much more simplified approach, and again there is one-to-one analogy between heat and mass transport, and it is said that, well, we can say that mass transport is a first order process. So, therefore, we have a mass transfer coefficient, and that mass transfer coefficient is Km, and this Km multiplied by area multiplied by the driving force delta Ci essentially gives us the net rate of transport. Just like the way I said that the net rate of heat transport is equal to heat transfer coefficient into the area through which heat is flowing and multiplied by the temperature differential which drives the heat transfer. In the case of mass transport, we have, so this you can see the similarity. So, the heat flux was q dot, and then this is equal to h into A into delta T. So, that was the rate of heat flow, and now Ni represents the rate of mass flow, and in which Km represents the mass transfer coefficient. H is the heat transfer coefficient, Km is the mass transfer coefficient. H was a function of fluid flow, Km is also a function of fluid flow. So, therefore, Km cannot be known unless and until we have idea about the fluid flow. So, indirectly through these expressions, through such expressions we incorporate, or through Km we incorporate the influence of fluid flow in the system itself. So, in convective mass transport, therefore, the main objective for calculation of mass transport rates boils down to the calculation of the convective mass transport coefficient. Okay, if you can somehow calculate Km, in that case delta Ci will be known to us, and this is a very interesting. The concepts of thermodynamics really comes here in order to find out what that delta Ci, and I am going to explain to you subsequently when we talk about metallurgical kinetics. The area which is relevant to transport will be always known to us, and therefore we should be able to calculate without much difficulty the rate, provided we know the mass transfer coefficient. Now, just like the way we had a free convective heat transfer and forced convective heat transfer, we have free convective mass transfer and free forced convective mass transfer. So, because of solutal concentration gradient, just like the way because of thermal gradients we have density difference in the system which precipitates into some kind of a weak convection current which we call as free convection. Now, in the case of mass transport also, if you have concentration gradients in a fluid, and that concentration gradients can precipitate in density differential, and again this density differential can induce some kind of a weak motion in the system. So, this is called solutal convection. Now, if you have both free convection heat transfer and free convection mass transfer, because of temperature difference as well as because of concentration difference, we call that convection as thermosolutal convection. For example, the continuous casting, if you go towards the lower part of the bloom or the billet, where there is virtually no stirring effect felt of the material coming through ACN, there whatever flow you are going to see, weak flow, that would be basically due to your thermosolutal convection, because there is going to be temperature differential in the fluid as well as concentration difference in the system. So, if we have forced convection heat transfer, so here we had forced Nusselt's number as a function of Reynolds number and Prandtl number for forced convection, and Nusselt's number is equal to function of Grashoff's number and Prandtl number in the case of free convection. Similarly, we have in the case of mass transport, we have in place of Nusselt's number what is called as Sherwood's number, a function of Reynolds number and Schmidt number, and Sherwood's number as a function of Grashoff's number and Schmidt number. This is called often the that material Grashoff's number, and this is a thermal Grashoff's number. So, there is some difference between the two. So, it boils down to in convective mass transport that we have to have a correlation, and based on that correlation we should be able to calculate the corresponding Sherwood's number, because we assume that the flow will be known to us, and once we know the flow, we know the Reynolds number, and once we know the Reynolds number, Schmidt number is equivalent to Prandtl number. Only thing is, in Prandtl number you have thermal diffusivity, in Schmidt number you have mass diffusivity. So, if you know Reynolds number, that Schmidt number is known. If a correlation is available, you will be able to find out what that Sherwood number is equal to, and once you know the Sherwood's number, you will be able to find out that what is the mass transport coefficient. And once you know the mass transport coefficient, the task is now simple, and you multiply that mass transfer coefficient with area, and you get the net rate of transport of I. This now needs to be explained a little bit, that how do we obtain the differential concentration which is driving the mass transport in the system. Now, there is a lot of analogy between heat and mass transport. Therefore, many a times the correlation which is derived for some simple situations in heat transfer, they can be applicable in a straightforward manner to mass transport also. For example, I have given you the Range-Marshall correlation for heat transfer. Similarly, the Range-Marshall correlation for mass transport is, which is valid for laminar flow, for spherical geometry. So, you can see the analogy between heat and mass transport, the characteristics between the similarities between thermal and concentration boundary layers, and the similarities between the correlations. So, for every situation in mass transport, therefore, we need not have to have a correlation. If a heat transfer correlation is available, we can convert that or make that correlation applicable to mass transport also. Alternatively, if we do not have correlations available for any given situation, we have no option but to go back and carry out experiments and derive the correlation. So, now let us look at the mass transport and chemical reaction on which the concentration really concentration differential really is, on the basis of which concentration differential is estimated. Now, suppose let us look at a metallurgical process, a mass transport process. Suppose we have an interface, and this interface is slag is here and metal is here. Suppose we have, so this is I say slag because I am going to use S and metal, and then we have sulfur in the metal, and eventually we have sulfur 2 minus in the slag. So, we have oxygen 2 minus in the metal, and what happens is that we get oxygen in the metal. So, how does the reaction, what is this imply? This implies, for example, calcium oxide. So, this is the slag metal reaction, which I can represent as S in metal plus O 2 minus in slag, and if I consider the equilibrium for a moment, and then I write S 2 minus in slag oxygen. So, this is the reaction, chemical reaction. And now, if you look at it, this reaction essentially implies that this is phase 1 metal, this is phase 2. So, it is a heterogeneous chemical reaction, and this heterogeneous chemical reaction now takes place at this phase boundaries. In order that the reaction takes place at the phase boundaries, we would like to have sulfur from the bulk moving to the metal. We have to have oxygen ion meeting slag metal interface. Then a chemical reaction takes place, and once the chemical reaction takes place, sulfur moves to the slag and oxygen moves to the metal. So, now you see the desulfurization can be clubbed into 4 different kinetic steps. So, we are gradually getting into the subject of metallurgical kinetics, and then we will see the relevance that how can you calculate these terms. So, let us remember this. We will discuss kinetics, get back here and then do the rate calculation to explain the matter better to you. So, the entire process of desulfurization is comprised of 4 different mass transport steps. Mass of sulfur transfer from bulk to the interface, oxygen ion transfer from the bulk of slag to the interface. Then these are the 2 mass transport steps. Once these have occurred, then the chemical reaction takes place. Okay? And after the chemical reaction, again sulfur is from the interface is moved into the bulk of the slag, and oxygen is moved from the interface to the bulk of the metal. Because if we allow oxygen and sulfur to accumulate at the interface, then what is going to happen? The reaction is going to come to a halt. Okay? The reaction will not proceed. So, what we are talking about now is not equilibrium, but continuous transfer of sulfur. So, the continuous transfer of sulfur essentially, as I have mentioned, are comprised of 5 different kinetic steps, of which 4 are mass transfer, okay, transfer from bulk to the interface or moving from the interface to the bulk, and 1 is the chemical reaction. So, these are called the individual kinetic steps, and the rate of the desulfurization is going to be a function of the rate of the individual kinetic steps. What does that mean? That this mass transfer of sulfur from the bulk to the interface will also have some rate. Maybe it is a convection is taking place. So, I will find out that what is the rate of transport of this. I will have to calculate the flux, convection flux or convection plus diffusion flux. So, there is a rate of net rate of transport 5 kg moles of sulfur per second to the interface. Similarly, I have a rate of transport for this. I have a rate for chemical reaction also, forward reaction. So, all the 5 steps that I have just now mentioned, they are all associated with their individual rate, which essentially, and this is called the intrinsic rate of each of the kinetic processes. So, for example, now I give this example in the classroom, that suppose you stay in you are a student, you stay in your hostel, and your hostel is quite far away, you have a bicycle. So, to attend to the class at 8 o'clock, suppose you get up at 7:30. So, you take 5 minutes to brush up, another 10 minutes to have your breakfast, and then another 10 minutes to bike down to the classroom to get there 5 minutes before time. So, 10 plus 10 plus 5. So, these are the time taken for the 3 individual steps, and the total time that you take to reach the classroom from your hostel is a summation of all these activities. Okay. Similarly, the rate, overall rate of desulfurization there here we are going to see is the summation of the rate of mass transport, summation of this rate of 4 mass transport steps, 2 in the metal phase, 2 in the slag phase plus. Now, it may be possible that the rates are not comparable. Some rates are very high, some rates are very slow. Now, the slow step is going to control the rate of the process, because these are all operating, these kinetic steps are all operating in series. What do I mean? That if I stop one of the kinetic steps, and kinetic steps means the individual steps, transfer of metal from sulfur from bulk to the interface. This is one simple kinetic step. So, if I stop one of these steps, 5 steps, any of the 5 steps, the process of desulfurization or the mass transfer of chemical reaction, which essentially is the desulfurization, will come to a standstill. So, when the processes are connected in series, individual kinetic steps are connected in series, it is the slowest step that is going to determine the rate. For example, I go back to that classroom problem, and now I say that you take 2 minutes to brush your teeth, to get freshen up and dress, 5 minutes to have breakfast, and then 20 minutes to bike down from your hostel to the classroom. That means these activities, okay, the efficiency with which you carry out these activities are not same. the biking takes much longer time than fresh, eating your breakfast or getting up from the bed itself. So therefore, I can say that look, if you can now, instead of biking, if you bicycling, if you can buy a motorbike and then expedite the rate, you should be able to reach the class much faster. Okay, so if you are biking, use a motorbike, in that case maybe you should be able to reach the classroom in about just 2 minutes of time, and then you say that again, now my rates are comparable. One is 2 minutes, second is 5 minutes, and with a motorbike also it is 2 minutes. So in 9 minutes I should be able to get to my classroom. But alternatively, in the previous case, if bicycling takes 15 to 20 minutes, in that case you can say that, well, this is the slowest step, and this is the reason why I am getting late to the class. I cannot possibly be more efficient in terms of brushing my teeth or getting dressed up or eating breakfast, but if I can somehow expedite my travel time from the hostel to the classroom, maybe I should be able to reach the class in time. So therefore, when the steps are connected in series, the slowest step determines the rate, and in metallurgical kinetics, often we are concerned with determining the slow kinetic step. Now, it is not necessarily that the rate of a process is going to be controlled by one single kinetic step. So if I can identify per se that out of these 5 steps only one is rate limiting, this could be either a mass transfer step or a chemical reaction step. Okay, forget about mass transfer in metal or the slag, we are not talking about it, but essentially the nature of the desulfurization process gives us 2 types of kinetic steps, mass transfer and chemical reaction. So when both mass transfer and chemical reaction both control the rate, that means the individual intrinsic rate of these processes are identical, then we say that it is a mixed control scenario. So the possibilities are 3. Either the process could be mass transport control, or the process could be chemically controlled. When you say chemically controlled, it means the mass transport steps are very, very fast, the chemical reaction itself is very, very small. Okay? Or third possibility is that both mass transport and chemical reaction can be rate limiting and they control the rate. Now, the rate of chemical reaction, let us now generalize the subject. The rate of chemical reaction, okay, at elevated temperature follows what kind of a law? Arrhenius rate law, A exponential Q by RT. Therefore, this tells us that as temperature is increased, the rate of the chemical reaction increases significantly. So therefore, the rate of a chemical reaction, okay, so we have 2 mass transport step before this chemical reaction, 2 mass transport step after this chemical reaction, and now we are looking at just this one step, and we conclude that look, based on the Arrhenius rate law, we can expect that the rate of the chemical reaction under still making condition where temperature is 1873 Kelvin could be really very, very fast. Very, very fast. If the rate of a chemical reaction is very, very fast, what does that mean? That means the process will tend to reach equilibrium very, very fast, and therefore we can say that under that condition, as a thumb rule, we can say that chemical reactions would be operating under equilibrium condition because the rate of the chemical reaction is fast. Does that mean there are no exceptions? Yes, there are few exceptions where chemical reaction even at high temperature is rate limiting, but that is besides the point. So now we have, so if the moment we say that chemical reaction is rate limiting, and then we have 4 different mass transfer steps, and out of that, if I say that look, I do some analysis, there are kinetic analysis based on which I can say that, well, it is not the mass transport in the metal phase which is important, it is mass transport in the slag phase that is much more important. So all the mass transport, I can say that everywhere there is no mass transport here. The moment I say that mass transport in the metal phase is not rate limiting, it is very, very fast. What does that mean? If the mass transport is very, very fast, there is no concentration gradient of sulfur in the metal itself. There is no concentration gradient of oxygen in the metal itself because mass transfer is very, very fast. Okay, that means everything is very well mixed. So whatever is coming into the metal, it is immediately getting mixed. So therefore, we have a homogeneous concentration here. Okay, so the moment we make these assumptions, we can make certain idealizations, and then we can say that the interface concentration is equal to the bulk concentration, or the bulk concentration is the. Let us quickly look at this scenario. For example, Now, heat transfer, for example, I have a solid surface. This is it at a temperature of T sub 0, and this is a fluid flowing T sub B. Okay? We know that ahead of a solid liquid interface, so the fluid is flowing like this, we have a thermal boundary layer like this. This is called TBL, briefly, or thermal boundary layer. So, this is temperature is equal to T0, and then the thickness of the boundary layer basically is defined as where the temperature becomes almost equal to 99% of the bulk temperature. Now, basically what we see that heat is being transferred from the bulk to the solid surface, and I can now split it into two parts. One is, this is the boundary layer. This is not boundary layer, this is the thermal boundary layer, and this is T versus X plot. So, heat is going to be transported now from the bulk to the surface, and I can split it up into two different parts. I can say, look, heat is transferred from the bulk to the interface, and from the interface then through the thermal boundary layer. Now, the moment I say this, I can say that the rate of heat transfer is controlled by, I can make this assumption that there are two steps which controls the rate of heat transport in the bulk phase as well as transport within the boundary layer. It is true also for mass. Same example I could have given in the context of solid liquid mass transport also. And now, if I say that, look, I will make an idealization, not two steps control the rate, I will say that the rate is controlled by mass transport within the boundary layer, because the boundary layer gives the largest resistance. The velocity is very small here, velocity is very large here. So, there nice, it boils down to saying that heat transfer from here to the edge of the boundary layer is almost instantaneous. It boils down to that there is no temperature gradient, and that is why we always take, if you remember that when you determine the rate of the process, you may have calculated that temperature far away from the interface. What is that? That is the bulk temperature, and the driving force for temperature is the surface temperature, and a temperature which is far away from the solid surface. This temperature is far away, but this temperature actually prevails up to the edge of the boundary layer, because of the simple fact that we have made an assumption that the transport of heat within the bulk is instantaneous, and that there is no concentration, there is no temperature gradient. The largest gradient really occurs within the boundary layer itself. So, the actual curve is then idealized in this particular fashion, and we see that between the edge of the boundary layer and the bulk there is no drop, and that is how we determine the temperature also. Now, we are going to see that how this concept boils down to in the case of a mass transfer. Now, suppose I have a solid here which is dissolving into liquid. So, instead of T0, now I say that look, there is C here concentration, and this C solid gets into, C is in the solid, and this solid gets into C into liquid. Or I can say this dissolves. There is a fluid which is flowing past the solid surface, this is the solid surface, and there is a fluid which is flowing past the solid surface. So, C from the solid is continuously getting dissolved into the fluid. This is the reaction, C in the solid phase getting to C, and what does this reaction is taking place? This reaction is taking place at the edge of the solid or the interface, solid liquid interface, which is this particular line. It is here that this chemical reaction is taking place. So, the overall rate of the dissolution of this plate or overall rate of C transport to the liquid will be, first the chemical reaction has to take place, and then the fluid has to remove that, okay, and that is going to be distributed in the bulk itself. So, I can say that, well, this is the solid, and similarly I can have a concentration layer, concentration boundary layer developing. So, this is the CBL concentration boundary layer, this is the distance x, and this is the concentration. So, therefore, now we can say that look, far away from the interface, it is the bulk concentration, but this bulk concentration I can assume it to prevail up to this particular interface. I have made this assumption that within the bulk the concentration, there is no concentration gradient, the mixing is very rapid. It is true, because in the bulk the agitation, level of agitation is far intense than it is near the wall itself. So, therefore, the driving force of concentration becomes, this is Cv is known, but what is this concentration here? So, that determines the driving force for concentration which I have used in this particular expression. Now, I will assume that the rate of dissolution, the rate of solid from the solid going into the liquid depends on the rate of mass transport, depends on the rate of this chemical reaction, plus the transport of the species from the boundary through the boundary layer, plus the transport from the boundary layer to the bulk. But the third step does not exist. The transport is determined by only two steps, the rate of the chemical reaction at the interface plus the transport across the boundary layer. I apply my judgment of high temperature kinetics, and if I say that look, if the process is occurring under high temperature, okay, in that case I can say this equation will be close to equilibrium, and if this equation is close to equilibrium, therefore the rate of mass transport is going to be dictated totally by the rate of boundary layer or transport through the boundary layer itself. Now, the moment I say that this chemical reaction is under at equilibrium, we can apply our knowledge of thermodynamics and say we can write down that K equilibrium is equal to activity of carbon or activity of C, okay, in the phase, and then activity of C in the solid phase. And if I know now K equilibrium from my delta G naught value at that particular temperature, I should be able to find out, or if it is a dilute solution, I can say it is wet percentage of C divided by activity of, if it is a solid phase, pure solid phase, then you say this is equal to 1. Okay. So, therefore, if you know delta G naught, because delta G naught values will be known maybe from Millingham diagram type of diagrams or from thermodynamic data book. So, knowing the temperature, I will be able to calculate delta G naught is equal to minus RT ln K, K equilibrium will be calculated, and this wet percentage of carbon at the interface, okay, this concentration will be known to us. So, while in the case of heat transfer, we are going to determine the surface concentration by using some kind of a pyrometer or thermometric devices. In the case of mass transfer, often the interfacial concentration is going to be determined through thermodynamic considerations.